Hello, everyone. Let's begin today with something you've surely noticed: the tiny cube shaped crystals of common salt on your dining table. Have you wondered why they form such neat little cubes? The answer lies in the symmetry of the cubic system, one of the 7 crystal systems in solid state chemistry. In a cubic lattice, all 3 edges are equal: A equals B equals C, and all the edges alpha, beta, and gamma are 90 degrees. The cubic system can exist in 3 forms: the simple cubic, the body-centered cubic, and the face-centered cubic. Each differs in how atoms occupy positions inside the cube. Polonium crystallizes in a simple cubic form. Cesium chloride follows a body-centered structure, while sodium chloride and many metals adopt the face-centered arrangement. Let's dive deeper into these fascinating geometries.
In the simple cubic system, also called a primitive cell, atoms are positioned only at the 8 corners of the cube. But remember, these corner atoms are not entirely owned by one unit cell, each is shared with 7 neighboring cubes. That means each corner contributes only 1/8 of an atom. Multiply that by 8 corners and you'll see that a simple cubic unit cell contains just 1 atom in total. Because of this loose arrangement, the packing efficiency is quite low, only about 52.4%, with almost half of the space empty. This inefficiency is why simple cubic structures are rare in nature. Polonium is one of the very few elements that crystallize in this way. Now imagine that in addition to the 8 corners, there's also one atom placed right at the center of the cube. This is the body-centered cubic structure, or BCC. Just like before, the 8 corners contribute 1 atom in total, and the body center atom belongs completely to the unit cell, making the total number of atoms per unit cell equal to 2. The packing efficiency here improves to about 68%. Because of its tighter arrangement, this structure is adopted by important metals like iron, chromium, and tungsten. Their hardness and relatively high melting points are explained beautifully by this body-centered arrangement. Next comes the most efficient arrangement, the face-centered cubic unit cell, or FCC. In this case, atoms are located not only at the 8 corners but also at the centers of the 6 faces. The corner atoms together contribute 1 atom, while the 6 face-centered atoms contribute 3 more, making a total of 4 atoms per unit cell. The packing efficiency rises to an impressive 74%, the highest among cubic systems. That's why many stable structures such as sodium chloride, copper, aluminum, silver, and gold follow this pattern. If you picture oranges stacked neatly in a supermarket pyramid, you're essentially visualizing the FCC arrangement. To understand why different cubic systems have different numbers of atoms, let's quickly revisit the rules. An atom at a corner is shared by 8 unit cells, contributing 1/8. An atom at the center of a face is shared by 2 unit cells, so it contributes half. A body-centered atom belongs entirely to one cell, contributing 1 full atom. An edge-centered atom, though less common, is shared by 4 unit cells and contributes 1/4. These sharing rules allow us to calculate Z, the number of atoms per unit cell, which is 1 for simple cubic, 2 for BCC, and 4 for FCC dot. Now let's look at how efficiently atoms are packed inside these cubes. The fraction of space actually occupied by atoms is called packing efficiency. It is calculated as the volume occupied by atoms divided by the volume of the unit cell, multiplied by 100. In a simple cubic arrangement, the efficiency comes out to 52.4%, leaving 47.6% void space. In a body-centered cubic structure, the efficiency is 68%, and in the face-centered cubic arrangement, the atoms occupy 74% of the space, leaving only 26% void. This explains why metals like copper and aluminium adopt FCC. It gives them the maximum stability and density. Finally, let's see how we can calculate the density of a crystal. The formula is density equals Z multiplied by M divided by Na multiplied by a cube. Here, Z is the number of atoms per unit cell, M is the molar mass, Na is Avogadro's number, and A is the edge length. For sodium chloride, which crystallizes in a face-centered cubic lattice with Z equal to 4, substituting the molar mass and edge length gives a density of about 2.16 grams per cubic centimeter. This matches the experimental density, which beautifully validates the structural model. So let's wrap this up with a quick recap. We explored the 3 types of cubic systems: simple cubic with 1 atom per unit cell and 52% efficiency, body-centered cubic with 2 atoms and 68% efficiency, and face-centered cubic with 4 atoms and 74% efficiency. We learned the sharing rules for atoms, derived radius-edge relations, and calculated density using the formula RHO equals Zm divided by Na, a cube. These concepts explain why real-world solids like iron, copper, and sodium chloride have the properties they do. I hope this session has helped you connect geometry with matter at the atomic level. In our next class, we'll move on to imperfections in solids and how they affect material properties. Until then, keep observing the crystals around you. Even the salt on your food is a story of perfect atomic architecture.